But if I were to claim that now, because if I change that, my time is going to go from order of e plus v squared to e plus v log v, or order n plus n log n, then I will have a mistake in my conclusion here. And I want you to find that for me. What are we missing out? So I said if we don't use a heap, if we use a plain array, then this is the time, right? And so that built up the motivation for doing that a little faster. So we said we could use a cube, we could use a heap, and that will take a log n time here. And if we do that, then if we were to claim that it's now going to take order of n plus n log n time, then that would be a problem. So what are we missing here? So look at this algorithm, and where else are we doing anything that would change based on the data structure? So essentially all I did was I changed the data structure from an array or a list to a heap, right? And we said based on that, this is now going to go down, but is there something else that's going to go up that we have to now take into account?
You're searching for V and Q?
Oh, which line number is that?
9.
No, actually not. It's not a... So, good question. These are all implementation-based questions. So all detailed questions are good at this point. But it could, but I can argue this way, that I will keep an array of vertices. I will initialize all of them to 0, which would say that they're on the right-hand side. As I bring them to the left-hand side, I will mark it as 1. So when I want to check is it on left-hand side or right-hand side, I do a constant time array check, right? So this does not take any time, whether in the first version or in the second version. But good question. So what else? So again, let me repeat the question. I said, first of all, we analyzed it. We said if we don't use a heap, then this takes this much time because of this time here, this time here, this time here. And then we said if we change an array to a heap, then this time goes down. Extractment goes down from order n to order log n. But my question is, what else is affected?
Is it the time to build?
Heapify?
Good point. Yes, that's point 2. But then I could say that a heapify actually only takes order of n time. To build an initial heap only takes order of n time. So that is essentially no different from then just putting that in a list. There might be a constant hidden there. So building an array is maybe really n time, while a heapify might be 5n time, but it's still order n. So asymptotically it's no different. There are only 9 or 10 lines or 11 lines of this program, so we should be able to go down one by one. And after 11 wrong answers, we will have a right answer. Which line number is affected by my changing the array to a heap?
11?
Exactly. So
take the priority?
Exactly. So now in a heap, if we now put all the numbers in a heap there, then we are now saying the key of v, which is a label, we said the label of v is less than the key, then we are going to change that, right? So we are going to decrease the, and this is a minimum heap, right? So we are trying to keep the minimum elements at the top. Now we are decreasing the label of a node. So that means we have to pay the priority, we have to pay the cost for that. And that takes how long time? How long time does that take in a binary search tree or in a heap? Let's call it a binary heap. That's what we're referring to here. How long time does that take? What are the heap operations? Extract minimum, it takes order log n time. Insertion takes order log n time. Searching takes long time, but we're not doing any searching. And we never discussed this one earlier, by the way, right? We never discussed this operation called decreasing or increasing, depending on what kind of heap is it. So you just have to I guess you can't remember, you just have to think about it. What is the answer? If you have a minimum heap, it's a binary heap, and you decrease you have a node and you decrease its priority or its value, then how long does it take to readjust the heap? Log n, right? So it's still a log n operation. You have a heap, you will simply, percolate upwards if it needs to be, or if its value is higher than its parent, then it'll stay there, right? That's all you have, right? It's not a complicated thing because you have a heap. You have if this is what your heap looks like, if this is the value for which you're changing from 9 to 6, then you will compare it now with the parent, and you may do some reordering here to make that correct, right? And let's say even if you had some other node here, let's say this node was a 7, and you change this 9 to a 6, then 6 cannot be a child of 7, so you'll switch them. And can you be sure that you have not bothered anybody else? You're fine, right? All the other nodes were obviously greater than 7, so they'll be greater than 6 as well. So you're fine. And this, you're not bothered by the order between the siblings, right? So you'll simply go towards the root, and you'll take order of log n time. So now we have to make a correct conclusion. So we said doing this with an array, it takes an order of order of v squared time. Now, if I change this to an array from an array to a heap, then how long will this algorithm take? And I'll wait for the answer. So how long does this algorithm take now? So how long we can just go through the steps, right? Can somebody tell how long does it take? Okay, Jennifer, go ahead.
E plus 1 log n.
Sorry, could you say that one more time? E plus?
E plus v log v plus log v.
I got to the E plus V log V part. What's the last part?
Log v.
E plus V log V plus log V. Well, then I can ignore the log V part, last one, right? So it would be E plus V log V. I'm not sure if that's correct, but seems to be close, but I don't think that's correct. Could you rerun your analysis? Okay, Chris, go ahead.
I wasn't really volunteering, but is it, I guess for the first part would be V, then...
So for the first part you mean the line, this actually might be the right approach. Let's just go down this way. So you're saying for first part meaning the lines 2 and 3?
It'd be V because you're going through all the vertices.
Okay, so lines 2 and 3 takes order V time. Keep going.
Then you do plus, then you go through the loop part, which is 6.
Okay, 6 onwards, yeah.
6 onwards. Would that be, since you're going through the edges, at least once, it'd be like E, log, E.
So Jennifer,